All right, so in this next segment, we're going to take on some exceptions. When you're drawing Lewis structures, we talk about the importance of getting a full octet, but it turns out in some cases that's not quite obeyed. Again, we're dealing with the Schrodinger equation. There's a lot of complicated stuff going on. So let's look at some of the possible exceptions you can have. Let me share the tablet and we'll take a look at that. So the learning objectives in this segment are to predict Lewis dot structures for molecules with too few electrons to fill the octet. There simply aren't enough electrons around. And also predict Lewis dot structures for molecules with an expanded octet. There's some cases where you can actually get a little more stable by having more electrons that are in the octet. That'll only happen with structures that are lower down on the periodic table when there's a little more energy available for the electrons to swish around. Okay, so incomplete octet, that's the first set we're going to be looking at. Let's look at boron tetrafluoride. So let's count up the electrons there. 3 plus 7 plus 7 plus 7. That's a total of 24 electrons. Let's draw the boron. That's the least electronegative, so that's going to be in the center. So there's 24 electrons. And we've written out 3 in bonds. That leaves 18 electrons. So let's write, we fill in the 18 electrons from, just fill them in the periphery. And we notice that we've used up all the electrons. We've used up all the spare electrons. And we're not satisfying the octet from boron. Boron doesn't have a full octet. So the instinct would be, well, let's pull some electrons from fluorine and make a double bond to boron. But it turns out that that doesn't happen. Because boron is that is a case that boron, because it's lower on the periodic table, it actually costs too much energy to lower down. It doesn't have that many valence electrons. It's a long way from the octet. It costs more energy to pull that, that lone pair off of fluorine and give fluorine a partial formal charge. So, let's look at the formal charges that you get right here. So in this case, fluorine's formal charge is 7 minus 6 minus 1/2 times 2, which is 0. So this grate has 0 formal charges. And if we look at the boron, then boron is valence of 3 minus 1/2 times 6, 3 equals 0. It actually has 0 formal charge. In order to get boron up to a full octet, if we shared that lone pair with fluorine, let's see what it would look like. So you have boron, fluorine, 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 and we make a double bond here. So now boron has a full octet, and that's what this would look like. Let's check to make sure it has the right number total of electrons. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons in lone pairs, and 8 electrons in bonds, 24 electrons. Okay, so that's a valid Lewis structure. So the formal charge on these two fluorines stays the same, and the formal charge on the boron is now 3 minus 1/2 times 8, since there's 4 bonds, equals -1. So there's a -1 on boron, and the fluorine is 7 minus 4 minus 1/2 times 4, which would be +1. So the fluorine is a +1 here. So even though we have a complete octet here, the formal charges are not very happy. And it turns out, how do you know which is the more important aspect, to have good formal charges or to have a full octet? Well, with boron, we know that the answer is it will prefer to have the correct formal charges and not have a complete octet. Is there any way to know that ahead of time, that, have in these conflict between the two rules, which one is more important? No, you just have to know that boron is an exception. Boron favors having better formal charges versus having a complete octet. Okay, so that's one exception where you don't quite have enough don't have quite enough electrons. Let's look at another case where you might not have enough electrons. So NO, that is not the word no, that is a nitrogen bonded to an oxygen. So let's write the Lewis structure for that. There's 5 plus 6 equals 11 electrons. So right away, you should see there's a problem brewing. Let's get to it. If we have 11 electrons, NO, let's start out with a single bond between them. That means there's 9 electrons we have to place. So we place them around the periphery. 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoa, 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 whoa. Okay, we've run out of electrons. We can't actually have a lone pair on another lone pair on the nitrogen. Whatever we do, we're going to have an odd number of electrons on one of the atoms. There's no way to get around that. So we're not going to have a full complete octet. So we can do better than this though, because the nitrogen only has like 5 electrons around it. We can make it a little more comfortable by taking 2 of the electrons. Oops, there's too much there. 2 of the electrons in the oxygen and donating them into the center. So now we have, we've got a total of 1, 2, 3, 4, 6 electrons in lone pairs, and 7 electrons, I miscounted. 7 electrons in lone pairs and 4 electrons in bonds for a total of 11 electrons. That looks good. It's the right number of electrons. And oxygen has a complete octet, and nitrogen is 1, 2, 3, 4, 5, 6, 7. 1 electron short of the octet. So somebody's got to be short. We got 2 possibilities. We've got N double bond 0, that, and we've got N double bond 0, 1, 2, 3, 4. Okay, we got these 2 possibilities. So which one is more favored? Because no one's going to have a complete octet. So we have to figure out what's the best way to put the electrons that we do have. So in this first case, then oxygen is going to have 6 minus 4 minus 1/2 4 equals a formal charge of 0. And nitrogen is going to have 5 minus 3 minus 1/2 4 equals 0. Nitrogen has a formal charge of 0, and oxygen has a formal charge of 0. Whereas if we look at the other structure, we would get oxygen is 6 minus 3 minus 1/2 4 is going to be a +1 formal charge. Did I get that right? Yes, 6 minus 3 minus 2 is +1. And nitrogen is going to be 5 minus 4 minus 1/2 4 equals -1. So oxygen have a +1 formal charge, and nitrogen has a -1 formal charge. Given that we're going to have an odd number of electrons no matter what, and somebody's not going to have a complete octet, we conclude that putting the lone pair on nitrogen is the most stable structure. And chemically, experimentally, that is indeed what we get. Okay, so that's how we deal with 2 possibilities of too few electrons. Either you have an incomplete octet, and boron, I'll show you a couple of examples. Aluminum, is another example. We can have an incomplete octet. We'll look at a periodic table and look at the general locations later. Or you simply have an odd number of electrons. You have to figure out who's going to be without a full octet. So those are some cases there. So we've covered the main points you see in not enough electrons.